last time we saw which parameters we should check while selecting a MOSFET. This time we'll see how a MOSFET switching works and what all things are important for it. So let's start. We'll check the dynamic characteristics of the MOSFET right now. These parameters are very dependent on the condition that determine how we measure them. These are very helpful for switching applications and have a very crucial role which determine how fast a MOSFET can switch on and switch off. If we check a MOSFET, there are some parasitic capacitance and resistance present inside. If we see this simplified equivalent circuit of an N-channel MOSFET, we can see there are capacitance between gate to source, gate to drain, and drain to source, and resistance at drain, gate, and source. The gate to drain capacitance is also called as the mirror capacitance. This mirror capacitance is very important for switching characteristics because the CGS and CDS stay constant in the switching cycle, but the mirror capacitance changes. Well, we know when we provide VGS, the MOSFET turns on and VDS decreases across the MOSFET and current starts flowing through it. Now, this mirror capacitance is low when the MOSFET is turned off. But when the MOSFET is turned on, the VGS increases and VDS starts decreasing. There is a point where VDS becomes equal to the VGS, and at this point, the mirror capacitance increases to approximately 10 times the value of the time when the VDS was larger than the VGS. We'll see its significance in switching of the MOSFET. Combination of these capacitors make input capacitance, reverse transfer capacitance, and output capacitance. The input capacitance is tentatively equal to the mirror capacitance plus gate to source capacitance. This capacitance is actual parasitic capacitance between gate and source. The MOSFET turns on only when the input capacitance is charged fully, and it turns off when the input capacitance discharges. This capacitance value is mentioned in the datasheet with particular measuring conditions of VDS, VGS, switching frequency, and junction temperature of the MOSFET. Next is the output capacitance. It is tentatively equal to the mirror capacitance plus drain to source capacitance. This capacitance is the actual parasitic capacitance between the drain and source. The value of these parasitic capacitors should be as low as possible. To turn on a MOSFET, we need to use a gate driver circuitry, which can inject the gate source voltage to charge the input capacitor and provide a part to discharge it as well to turn off the MOSFET. The total gate charge, gate to source charge, and gate to drain charge are gate charges. They show how much gate charge is required to switch the MOSFET. More the required charge is, the more the switching time will be, which is not good. These characteristics are also mentioned in the datasheet with measuring conditions. So all of these parameters are called as dynamic characteristics of the MOSFET. Now we'll see how a MOSFET turns on and how it turns off and what happens with gate to source voltage, drain current, and drain to source voltage. We'll divide this operation on different time durations from T0 to T9. The MOSFET is turned on at time 0. We provide a gate to source voltage at the MOSFET. This voltage increases and it charges the input capacitor of the MOSFET with internal resistance of the driver circuit. When the threshold voltage of the VGS reaches at time T1, the MOSFET starts conducting. The drain to source voltage decreases across the MOSFET where the current starts flowing to the circuit and drain current increases. At time T2, the drain to source voltage becomes equal to the gate to source voltage, so the mirror capacitance has increased. The VGS remains the same, but the gate charge current is fed via the mirror capacitance to decrease the VDS. At T3, the input capacitance is charged up to drive the MOSFET. The MOSFET resistance further decreases, and at time T4, the RDS on of the MOSFET reaches the lowest value, and MOSFET is fully turned on. This is how a MOSFET turns on. Now after some time, the MOSFET turn-off process starts. To turn off the MOSFET, we remove VGS from the gate of the MOSFET. Well, the input capacitance is fully charged. So this capacitor starts discharging through the internal resistance of a driver circuitry. So VGS of the MOSFET decreases. At time T6, RDS on starts to increase slightly. The MOSFET acts as a mirror integrator at this point, which reduces the drain current in the MOSFET, and VDS of the MOSFET increases. Now at time T7, VDS becomes equal to the VGS. The mirror capacitance decreases to a small value. This mirror capacitor gets charged, and now the VDS voltage surges. The resistance is increased and drain current decreases. The gate voltage decreases up to threshold voltage at time T8. And finally, the input capacitor fully discharges in period T8 to T9. And MOSFET switches off. Well, MOSFET doesn't have accumulation time, so switching time is determined by the charging and discharging of the input capacitor. As we see, when we turn on and turn off a MOSFET, it takes some time, which is measured in turn on delay time and turn off delay time. This is the rise time. It is measured while the MOSFET is turning on, and this time is recorded when the VDS across the MOSFET decreases from 90% of its actual value to 10%. And fall time is measured when the MOSFET is turning off. This time is recorded when the VDS across the MOSFET increases from 10% of its actual value to 90%. Well, that's how a MOSFET switching works. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.